Okay, this is the last topic in series and sequences. And this last topic is a pretty fundamental key contribution to mathematics from Taylor and from Lagrange, two very um, famous mathematicians. So what we're going to look at now is something called the Lagrange remainder and a topic of error analysis. So we are going to be looking at how well some p sub n of x approximation of f of x works. And we're gonna be able to formally or get to a finite analysis of how well my polynomial approximation works. And this is a very valuable thing because if we're going to approximate something, if we're going to approximate a function, we want to know, is this valid to approximate? Is it not? Depending on how accurate it is. So if n doesn't approach, if n isn't infinite, if n doesn't approach infinity, so for finite values of n, p of n will approximate f of x very closely, but there will be some difference. So again, this is for n not being infinity, which is a reasonable assumption. Um, for finite values of n, p sub n will approximate f of x closely, but there's some difference, and we want to be able to find out that difference. And that difference we're going to call r sub n of x. It's the remainder that if we added to p sub n of x would let them equal each other. So in other words, um, p sub n of x plus this remainder sub n of x equals f of x. Well, this remainder is the difference between f of x and p sub n of x. So that is our error. Our error, absolute value of r sub n of x, is the difference between my function and its polynomial approximation. So the question is, how can we find r sub n of x? And we are not going to go through the derivation of this. It's a pretty sophisticated proof. Um, if you're interested, it's worth a little bit more research on your part and some conversations on our part. But instead, I'm just going to give you the equation for the Lagrange remainder. And again, the Lagrange remainder is our error. This is the difference between um, f of x and p sub n of x. That's what our remainder or Lagrange remainder equals. So, given some function, given some uh, given some function, we can find a Taylor approximation for that function. And take f of c plus our derivative at c times x minus c times the second derivative x minus c over 2 factorial x squared. You've seen this before. This is Taylor's formula. And what we want to do is actually, there's an error. I got this out of the book. But these x's here, those should be x minus c to the n. So just note that. Um, but we've seen this Taylor formula before. The remainder is given as such. The remainder for this Taylor formula is f to the uh, fn plus 1, which means it's the what this means. That's the n plus 1th derivative of my function evaluated at z, where z is some number between x and c, times x to the n plus 1 all over n plus 1 factorial. And this is Taylor's remainder theorem. or rather the Lagrange remainder using Taylor's formula. So Lagrange came up with this remainder. So some key components of this, just pointing it out, Lagrange remainder only exists when n uh, is finite. And so, let's say that, we're doing a Taylor formula for degree 3, n equals 3. Then in our Lagrange remainder, we would be taking the fourth derivative, evaluating it at some value z, where z is between x and c. Um, and z is, and we'll get to this in a little bit, z is going to be the value between x and c that makes our derivative the biggest, because we want to look at, what's our maximum error. And then multiplied by x raised to the n plus 1, all over n plus 1 factorial. So we're looking at the Lagrange, not the multiplier, the Lagrange remainder. The Lagrange multiplier we'll look at a little bit later in multivariable. This is still single variable calculus. So, a couple things. N is the number of derivatives that we're talking about. So in this case, n plus 1, we're taking n plus 1, the n plus 1th derivative, evaluated at z, some number between c and x, all over n plus 1 factorial x to the n plus 1. This will calculate how much error there is between our polynomial approximation and the actual function. Well, that's the Lagrange error. Taylor came up with his own inequality, which is very similar. And let's really focus on how similar they are. Taylor's inequality, and he's got this value m, where m is the maximum value. M equals the maximum value of our n plus 1 derivative at x. It's the maximum of this in between C and B, or B and C. So in other words, on the interval C to B, uh, this m value that's showing up here, this m value is the maximum n plus 1th derivative on that interval. And then the slight change is that instead of x, we've got b minus c, that we're looking at, over that maximum, over that entire range, b minus c raised to the n plus 1. And this b minus c, using the b minus c and using the m, what that does is it makes our error as big as possible. And we want to have, as big as possible of error, so to acknowledge this is the most error that we might have on that interval. And it's the most that there is, so any other error on that interval will be less than that. So we're acknowledging, what will be our most error. Let's actually put this to work. So it says let f be a function with 5 derivatives on the interval 2 to 3, and assume that our 5th derivative on x is less than 0.2. So in other words, let's start interpreting some of this stuff. It's got 5 derivatives. We know that our 5th derivative is less than 2, so our m value we're going to say is 2. That's the biggest our 5th derivative could be for all x in this interval 2 to 3. It says if a 4th degree polynomial for f at c equals 2, so when c equals 2, is used to estimate f of 3, how accurate is this approximation? Well, in order to answer this question, because we're just getting familiar with the equation, let's go back. I'm going to copy this and bring it over. So my error, r sub, well, we're looking at a 4th degree polynomial approximation. So r sub 4 of x absolute value, is going to be less than or equal to um, my maximum value of my fifth derivative on x, and that we know is 0.2. So 0.2 over n plus 1. Well, n is 4, so 4 plus 1 factorial times the absolute value of b minus c. So on the interval from 2 to 3, so that's 1 raised to the n plus 1, 5. So further simplification, we get that my fourth degree polynomial approximation uh, will have an error of less than or equal to 0.2 over 5 factorial. Um, and what does that equal? Well, uh, this is 0.2 over 120, which equals 1 over, I don't know, 600. Really, really, really small. So that's a very good approximation, um, and an approximation that we could feel pretty good about. So this demonstrates the use of uh, of finding the error. You know, we said if we only go for a fourth degree polynomial, which isn't much, it's very easy to generate that type of polynomial. If we only do a fourth degree polynomial uh, on this interval from 2 to 3, on this interval here from 2 to 3, evaluating, estimating the polynomial um, when c is 2, we are able to estimate with an accuracy of 1 over 600. So 1 over 600 is our maximum error, in other words. Let's go ahead and look at another example. Um, here's just the solution key, but we already developed that. Um, so we want to estimate the error that results when sine of x is replaced by x minus 1/6 x cubed. Well, this is our Taylor approximation for sine x. We've seen this before. This is n equals 3. So we want to find out what the error would be. So using the error for n equals 3, is going to be less than or equal to, well, we need to find our m value. Well, our m value is the maximum that f, our fourth derivative, uh, it's the maximum that my fourth derivative can be for x being between negative 0.2 and 0.2. So, well, we know that, you know, sine x is going to go to, this is my function, and then f prime would be cos, and then f double prime is going to be negative sine, and f fourth will be negative cos. Uh, so we know that my maximum value of this fourth derivative between 0.2, negative 0.2 and 0.2, the absolute value of that, that the derivative is going to be at most, the most that this can be is going to be 1. That's the biggest it could be. So we then can say that my error is going to be 1 because that's the largest my fourth derivative could be over n plus 1, so 3 plus 1 factorial times the absolute value of b minus c. So we're looking for x between um, absolute value of x less than 0.2. So the interval from b minus, the interval of b minus c, we can replace with 0.2, and that's raised to the n plus 1, or raised to the fourth. And if we were to, you know, evaluate this using a calculator or quickly doing some mental math, that this value is in fact, let's see, equal to 0.000067. So our error is less than or equal to 2.000067. So it's a very accurate approximation there. And we'll start with another video continuing on with this error analysis.